from Theoretical Computer Science Department at Jagiellonian in Krakow, Poland. There is 9 a.m. here, so we are slowly waking up. But I see Bartosz is already on campus, and I am really surprised. He recently spent some time working on geometric representation of graphs, structural graphs theory, and χ-boundedness for some classes of graphs. One of his recent results is omega times log omega bound for the chromatic number of graphs that are determined by intersection of rectangles. But today he is going to talk about another χ-boundedness result, exponential one this time. And yeah, you see the title, so I am not going to read it. And Bartosz, the floor is yours.
Okay, thank you. And thank you for giving me opportunity to speak at this event. I am going to speak about coloring polygon visibility graphs and their generalizations, which is joint work with James Davies, Tomasz Krawczyk, and Rose McCarty. So let me start with some basics. I'm going to denote the chromatic number of the graph by chi and the clique number of the graph, so the maximum size of a clique in the graph by omega. So this is standard notation. And it will always be clear what graph I'm going to refer to. So it will be referring to some specific graph. And we have this obvious inequality. Every vertex of a clique has to receive a different color in a proper coloring. So the chromatic number is at least the clique number. And on the other hand, it is well known that there are graphs with clique number 2, so graphs which have no triangle and still have arbitrarily large chromatic number. And actually, it is a very well-known result due to Erdős. Then we can force arbitrarily large chromatic number and arbitrarily large girth. So we can construct such graphs which don't have short cycles at all. Therefore, since we cannot have any bound on the clique number, on the chromatic number with respect to the clique number for general graphs, it makes sense to try to find such bounds for specific classes of graphs. So we will say that a class of graphs G is χ-bounded if there exists a function such that in every graph in this class G, the chromatic number is bounded by that function of the clique number. Okay, so in particular, the class of all graphs is not χ-bounded. And there has been a lot of research trying to understand which classes of graphs are χ-bounded. And in general, this research went in 2 directions. So on one hand, there is a consideration of some classes of graphs with geometric representations, whether they are χ-bounded or not. And this dates back to a work by Asplund and Grünbaum from 1960, where they proved that, like in modern terms, that the class of rectangle intersection graphs is χ-bounded. And on the other hand, there is a long direction of research about classes of graphs with excluded substructures. And we can say that it has been initiated by the famous Gyarfas-Sumner conjecture. So here is this conjecture. First, one more definition. We will say that if H is a graph, we will say that a graph is H3 if it contains no induced subgraph isomorphic to H. So we just exclude H as an induced subgraph. And then the conjecture by Gyarfas and Sumner asserts that for every 3T, the class of T3 graphs is χ-bounded. So we can exclude any tree as an induced subgraph, and then we will obtain a χ-bounded class of graphs. And this conjecture has been proved for paths by Gyarfas. This is a very beautiful result from the 80s, and also for many other special trees T. But in general, this conjecture is still considered to be widely open. And also, if we want to exclude a single graph, then in order to obtain a χ-bounded class of graphs, then we cannot exclude a graph that contains a cycle. So once again, this is this result by R dash, that there are graphs with arbitrarily large girth and arbitrarily large chromatic number. So whenever we exclude a graph which contains some cycle, we can take a graph with arbitrarily large chromatic number and with the length of the shortest cycle greater than the cycle that we have excluded. So as a corollary to this result by R dash, the class of H-free graphs is not chi-bounded if H contains a cycle. And also it is easy to prove that in order for this conjecture to be true for every forest, the Gerfash-Sumner conjecture, like for forests, is equivalent to this conjecture for trees. So this conjecture is kind of best possible. Okay, so I will return to that point in a few moments. Let me now go to the topic of this talk. So in this talk, I'm going to deal with classes of graphs with geometric representations, but also it will lead to some problems in classes of graphs with excluded substructures. So these representations which I'm going to talk about are so-called visibility graphs. So in particular, we can consider polygon visibility graph. So we have some polygon and vertices of the polygon, like in this picture here. These vertices of the polygon become the vertices of our graph. And two vertices are connected by an edge when they see each other within the polygon. So when the straight line segment connecting them is disjoint from the exterior of the polygon, then there is an edge. So, for instance, there is an edge between this vertex and this vertex here. We have this edge, even though there is a vertex in the middle, but this segment is disjoint from the exterior of the polygon, so we have that edge, okay? And the clique number of such a graph has a natural interpretation. We just look for the maximum size of a convex subset of points in our graph, which is entirely contained in the polygon. So in particular here, on these 5 vertices, we get a clique of size 5. Okay, so in 2005, Kára, Por, and Wood asked this question: is the class of polygon visibility graphs chi-bounded? And the main result of our work is a positive answer to this question. So yes, polygon visibility graphs, they are chi-bounded. They satisfy this bound, which is a single exponential in omega. Okay, so before I go further on to this chi-boundedness problems for polygon visibility graphs, let me make some detour and tell you the main problem that was studied in this paper by Kára, Por, and Wood. So this paper was focused on point visibility graphs. So this is another class of graphs where we have just points on the plane, and these points are the vertices of our graph. And the 2 points are connected by an edge if there is a direct visibility between them, so no other point obstructs this visibility. So here, for instance, we have an edge between this pair of points, but we do not have an edge between this point and this point, because on the segment between them, there is this third point here, which blocks visibility. So this was the class of graphs that they considered mainly. They proved that when the clique number is bounded by 4, that these graphs have a bounded chromatic number, and they asked whether this class of point visibility graphs is chi-bounded. So actually, it turns out that this class of graphs is not chi-bounded, and a construction with clique number 6 was provided by Fender a few years later. And what you can also observe about this class of graphs is that it is intrinsically not hereditary. Okay, because if we remove points, for instance, say that we remove this point from the graph, then suddenly this pair of vertices becomes visible and this pair of vertices becomes visible. So new edges are obtained, like new edges arise between pairs of vertices which we have not removed. So actually, it is not difficult to see that every graph is an induced subgraph of a point visibility graph. So if we take the hereditary closure, so hereditary, the class is hereditary if it's closed under induced subgraphs, right? So if we take all induced subgraphs of point visibility graphs, we will obtain like the class of all graphs. And yes, so in some sense, this χ-boundedness problems, this notion has been studied primarily for classes of graphs which are hereditary. So it seems that for this specific class of graphs, it may not be in some sense, this problem is kind of non-standard for this χ-boundedness study. Okay, so let's go back to polygon visibility graphs. They have been widely studied since the 80s, but apparently they are still not well understood. So here there is a couple of open problems about polygon visibility graphs. For instance, what's the complexity of recognizing them? Whether a graph is a polygon visibility graph? Is it in P? Is it in NP? We don't even know that, whether this belongs to NP. And what we also don't know is whether every polygon visibility graph can be realized by a polygon in general position. So like the points should be in general position, no 3 points on the same line, like here. This representation contains 3 points on the same line. And it is easy to see that this specific representation can be transformed to avoid this situation, right? It suffices to move this point slightly in this direction. Then the graph will be the same. It will be still the same polygon visibility graph, right? The graph will be isomorphic, but the points will be in general position. However, in general, we don't know whether this is equivalent. And you can also observe that this class of graphs is not hereditary either, because if we remove some points from the boundary of the polygon, then the polygon changes. It can change to something that is even no longer a polygon, because we want the polygon to be simple without any self-crossings. But here, on the other hand, if we take the induced, the hereditary closure of the class of graphs, we don't obtain all graphs. We obtain something that may be easier to look at by assuming that the boundary is just some closed curve without self-crossings, and we have some subset of points on this curve, and we want all visibilities, so all edges, to be disjoint from the exterior of that curve, the external region of that curve. Okay, so this way we obtain all induced subgraphs of polygon visibility graphs, and this is if and only if. Because on one hand, we can take this as the curve, like the polygon, and on the other hand, whenever we have a curve, we can just approximate it with a very fine polygon with a lot of vertices, and then take the induced subgraph of the vertices that we have selected. So these two classes, like curve visibility graphs, are induced subgraphs of polygon visibility graphs. Okay, but in this way we deal with the problem that the class of polygon visibility graphs was not hereditary, but we can also proceed further to a class of graphs which we understand slightly better, although it is a more general class of graphs. So instead of looking at polygons made of straight line segments, we can look at so-called pseudo-polygons. So we start with a pseudo-line arrangement, so an arrangement of infinite curves and unbounded curves, such that no two of them, like any two of them, cross exactly once, and any two vertices which are selected for our polygon, they should lie on a common pseudo-line. So for any two vertices on our picture, there should be a pseudo-line which passes through them, and by the first condition, this pseudo-line will be unique. Okay, so here you see an example of such a pseudo-polygon visibility graph. So the polygon goes along the segments of the pseudo-lines, and also visibilities go along the segments of the pseudo-lines. So for instance, this point 3 sees the point 5 because the visibility between them goes along this pseudo-line here, which is disjoint from the exterior of this pseudo-polygon. So of course, this is a generalization of polygon visibility graphs because we can take the pseudo-lines to be straight lines. And this is actually a proper generalization. So there are pseudo-polygon visibility graphs which are not polygon visibility graphs. And here we understand these graphs better. So for instance, O'Rourke and Stranu showed that recognizing these graphs belongs to the class NP. Actually, they considered a slight modification of this definition, something like vertex edge visibility graphs along pseudo-lines, where they actually find a polynomial time algorithm to recognize them. And also, a newer result is a characterization of this pseudo-polygon visibility graphs as cyclically ordered graphs. So I will be speaking about cyclically ordered graphs further on during my talk, but in general, you order the vertices along this boundary of the polygon. This gives some cyclic order on the vertices, and then we can look at some forbidden substructures which are excluded from these kind of cyclically ordered graphs, and provide a characterization of these pseudo-polygon visibility graphs by this kind of substructures. So they did it. Okay, and then we can do an analogous modification as I did with polygon visibility graphs. So instead of requiring that the boundary curve goes along the pseudo-lines, we can take just an arbitrary boundary curve, but the visibilities are still along the pseudo-lines. Okay, and this class of graphs actually represents all induced subgraphs of pseudo-polygon visibility graphs. So induced subgraphs of this give this, and this is again if and only if. And what we can also say about these curve pseudo-visibility graphs or pseudo-polygon visibility graphs is that we can assume that they are in general position without loss of generality. So here it is equivalent if we define them with the requirement that no 3 points lie on a common pseudo-line. Like here, these 3 points lie on a common pseudo-line, but we can avoid it. And we can avoid it for every pseudo-polygon visibility graph. So in some sense, they behave better, or we understand them better than polygon visibility graphs. Okay, so during this talk, I'm going to consider these visibility graphs or pseudo-visibility graphs as ordered graphs. So one way to view them as ordered graphs is to order the vertices cyclically, like in this picture, along the boundary, and then just look which pairs of vertices in this cyclic order are connected by an edge. Okay, but if we also say that we can cut this boundary line at some specific point, like here, suppose that here we make a cut, then we actually obtain a linear order. And then we can consider this kind of graphs as a linearly ordered graphs. So a graph equipped with a linear order on the vertices, like here, and then again we look at which pairs of vertices are connected by an edge. So these are 2 ways of looking at these graphs as ordered graphs. We either impose a cyclic order or a linear order on the vertices. And okay, so there is this result, which was proved by Ghosh in the 80s for polygon visibility graphs, but actually it generalizes to curve pseudo-visibility graphs, so these most general graphs that I have shown so far. Namely, Ghosh pointed out two kinds of cyclically ordered structures, let's call them patterns, which are excluded from these cyclically ordered polygon visibility graphs. So one of them here on the right, it's easy. They are all ordered wholes. So ordered cycles, like ordered in the same order as the cyclic order of the vertices, ordered cycles of length at least 4 with no chords. So these dotted lines here, they represent that these are non-edges. So they are excluded. But what is also excluded, and is kind of more complicated to explain, is structures that, like patterns that form what we call a family H. So suppose that we take two vertices which don't see each other, the vertex U and V, and this is a non-edge. And but if we go on one side of the cycle and we are able to construct this kind of, so say that we have U here, V here, and suppose that in one side of the cycle, we can construct this kind of alternating sequence of edges where each next edge starts earlier than the previous edge finished. Okay, so it can look something like this, so that we end up at V. Then this, in some sense, represents that that this part cannot block visibility between U and V from above. So like this part cannot enter from this part, from this way, from above, the segment between U and V, and cannot block this visibility. And like the same, if the same happens on the other part of the cycle, like we have these edges here, also from U to V, then nothing from below can block the visibility. And therefore, U and V should be visible. There should be an edge between them. But here, in this forbidden structure, there is no edge. And this is why the structure is forbidden. This is why it is an excluded structure. And I call it a pattern because some edges are specified so that they should appear in the pattern. This edge is specified so that it should not appear. And for some other pairs of vertices, for instance, this and this, like we don't care whether there is an edge between them or not. So like in these excluded patterns, we have three possible statuses of pairs of vertices. Either we specify that there should be an edge, or we specify that there should be no edge, or we don't specify whether there is an edge or not. Okay, so these two structures are excluded, and they are also excluded from curved pseudo-visibility graphs. Okay, so I will do again one digression here. So let's look at yet another class of visibility graphs, so-called terrain visibility graphs. So here we have this kind of X-monotone polygonal curve for terrain visibility graphs, like this one. And all the visibilities should go above this curve. So they are disjoint from the region below that curve. The pairs of vertices along the curve, they are still considered to see each other. So these kind of graphs, they are called terrain visibility graphs. And then we can make analogous generalizations of them to the pseudo-line arrangement settings and the setting where this curve, it's still monotone, but it does not need to follow the pseudo-lines. Again, the visibilities should be above that curve. And we obtain something that we can call the terrain pseudo-visibility graphs. And here we can also say something about now the linearly ordered excluded structures for these kind of graphs. And actually we can characterize them exactly using these kind of linearly ordered structures. So it follows from the results of Abello, Kumar, and Evans and Saidi that an ordered graph, now a linearly ordered graph, is a terrain pseudo-visibility graph if and only if it excludes the following ordered patterns. So one ordered pattern is that here it's on 4 vertices. It is exactly on 4 vertices. Here we have an edge. Here we have an edge. Here we have no edge. And here we don't care. So this pattern actually is a requirement that if this edge exists and this edge exists, then there should be this edge. Okay? Regardless of whether there are some other vertices here or not. And other excluded patterns are, as before, ordered wholes of length 4 and more. And this is actually if and only if. If an ordered graph excludes this set of patterns, then it is a terrain pseudo-visibility graph. So concerning this first pattern, we will call an ordered graph capped if it excludes this first pattern. So if an existence of such edge and such edge implies that there is this edge. If you know something more about these kind of visibility graphs, then perhaps you have encountered a name that that a graph is persistent. So persistent graphs are graphs which exclude exactly these two kinds of structures, and moreover, they have a Hamiltonian path which agrees with the order. So 1, 2, 3, 4, and so on. And they are these kind of persistent graphs have been widely studied in the context of these terrain visibility graphs. And these two conditions are exactly the conditions for persistent graphs. Okay. So here is the summary of like our results and the train of thought. So first of all, we have seen this theorem before, which is a generalization of Gauch's result, that when we look at curved pseudo-visibility graphs, then they exclude this family H, this strange family which was about blocking visibilities, and it excludes ordered wholes. So then what we can show is that whenever we have an H3 graph, cyclically ordered graph, then it can be vertex partitioned into 3 capped graphs. So graphs which are capped when, okay, we take the cyclic order on the vertices and just cut it off at some point to make it a linear order, and these graphs will be capped. So just to recall, capped means that this structure is excluded. Okay, so H3 graphs can be partitioned into 3 capped graphs, and then we can show that every capped graph satisfies this bound. And moreover, when it is ordered hole-free, then it satisfies this slightly stronger bound. The chromatic number is at most 4 to the power clique number minus 1. By the way, this first bound is provided that omega is at least 2, of course. So now the corollary to this is that every curved pseudo-visibility graph, so in particular every polygon visibility graph, satisfies this bound that I told you in the introduction. So why is it that? Okay, every pseudo-visibility graph excludes the family H and ordered wholes. So now we take this result. Since we exclude the family H, we can partition the graph into 3 capped graphs. But actually, because we excluded ordered wholes, then the graphs are not only capped, but they are also ordered hole-free. So they are both capped and ordered hole-free. So each of them can be colored with that many colors. And we just use separate sets of colors for the 3 of them. So this is why we get the factor of 3 here. Okay, so in the rest of my talk, I will first tell you something about this partition, but just I will tell you how it looks for polygon visibility graphs, not for general H3 graphs, but just for polygon visibility graphs, because it has a very nice geometric interpretation. And then, if time allows, I will tell you something about how we achieve this bound here. Okay, so first, let me go into this partitioning into 3 capped graphs. So we use this notion of weak visibility from an edge. So what is it? Suppose that we have a quite complicated polygon like this one, and we specify some edge of that polygon. So this edge here is fixed, it is specified. So we look at the subpolygon, which consists of all the points from the polygon and its interior, which see this edge, at least one point of that edge. But there is an additional requirement here that we don't want to include the part which is below this line. So we want that they see this edge, like in some sense from above, from the interior of the polygon. So what I mean is that I don't consider the part which is below, which sees this endpoint of an edge. Like this here is not included in that weak visibility subpolygon, which is a slight difference from the traditional definition of weak visibility, because the traditional definition of weak visibility, it includes this subpolygon here, which like the stuff that is visible from this point. Okay, but I don't want to include that. So let's take this subpolygon. So this is this is the stuff that is weakly visible from that edge. And then we can see that the other parts of polygon, of the whole polygon, can be partitioned into two kinds of what is called windows. So one of them are, in some sense, to the left, are left windows, and the others of them are right windows. So these blue ones, they are left windows because if we look, perhaps I should call them right windows, because if we look along this edge, which connects them to the weakly visible part, and this part is directed towards the edge from which the polygon should be weakly visible, then this and this is to the right of this segment when we look in the direction of the arrow. So here, as we look in the direction opposite from the arrow, it will be to the left. And here, they are on the other side. So to the left when we look in the direction of the arrow, and to the right if we look in the opposite direction. And what we can observe here is that two different left parts don't see each other. There are no 2 points in the left parts which would see each other. And the same in the right parts. There are no 2 of them which would see each other. So the visibilities are only between this central part and the left parts, this central part and the right parts, and between the left parts and the right parts. There may be some visibilities, but nothing more than that. So then we can recurse this partition. So now, for instance, we look at this polygon here, and we take out everything that is weakly visible from that edge. And then we obtain this subpolygon. And we recurse further and further. Okay, and we can now 3-color this kind of recursive partition in such a way that, for instance, if we have this as the root of our decomposition, then all the roots of the left windows will get the same color. They don't see each other. And the roots of the right windows, they obtain the third color, but again the same color, as they don't see each other. And then we recurse this kind of decomposition, and we obtain a 3-coloring of these weakly visible subpolygons with the property that 2 subpolygons of the same color, they don't see each other. No point of the one sees a point of the other. Like we have to adjust appropriately for what it means for the points like this one. This is considered a point of this polygon rather than a point of this polygon. Okay, so now we can color the vertices according to these parts. And this way, we have split our polygon visibility graphs into graphs which are induced subgraphs of polygon visibility graphs, like this one here, because now not on every vertex we have not on every vertex of the polygon we have a vertex of the graph, but they are visibility graphs of weakly visible polygons, and moreover, like if 2 points with the same color come from different polygons, then they don't see each other. So we can just restrict our coloring to a single of these polygons, like this one. Okay, so points from distinct polygons of the same color don't see each other. And now it turns out that according to our definition of weak visibility, it turns out that if we order the vertices, like if we cut the order along this edge to obtain the linear order, this edge from which we consider the weak visibility, then this graph is capped. And this can be easily seen here. So if we have these 4 vertices like A, B, C, D in this order along the boundary, and we have a visibility from A to C and from B to D, then A and D also see each other. So this is that partition into 3 capped graphs. So now it is enough. Okay, I show it to you just for polygon visibility graphs. An analogous argument would work also for pseudo-polygon visibility graphs, but for general H3 graphs, it becomes somewhat more complicated. But we can also do this kind of partition for general H3 graphs. Okay, so now it suffices to color these capped graphs. So we enter the area where we just have some assumptions on the excluded patterns in our ordered graphs, and we just ask whether the class of graphs which we obtain with these excluded patterns is chi-bounded. So here are some examples of this kind of lines of research. So for instance, suppose that we consider ordered graphs which exclude this pattern. What does it mean? It means that whenever there is an edge between vertices A and B and C in this order, then there should be an edge between A and C. So these graphs are comparability graphs. They are perfect. The chromatic number is equal to the clique number. Now look at this pattern. This pattern is just telling us that there should be a perfect elimination order. So this is a characterization of chordal graphs. And chordal graphs, again, they are perfect. So the chromatic number is equal to the clique number. Now, also, the graphs with this kind of pattern have been studied. They can be characterized as intersection graphs of rectangles, such that, for instance, the lower left corners of these rectangles, they lie on a common line. So they are chi-bounded by a result of Kalern-Suk. Then in this work, we have proved that something like this is chi-bounded. And there is also work by Pach and Tomon where they used these excluded ordered patterns to study chi-boundedness of some classes of graphs. So in particular, they showed that when this kind of pattern is excluded, then the class is chi-bounded with this quadratic bound. On the other hand, if we add one more excluded edge, like here we require that this is a non-edge, so now this is an excluded ordered path on 4 vertices, then this pattern gives a class of graphs which is no longer chi-bounded. And also there is a work by Aksenowicz, Rolin, Uckert, where they studied some patterns which are forests, and these are patterns without non-edges, so they considered these forests as excluded non-induced ordered subgraphs, and they gave some examples of such forests where the class is not chi-bounded. Yes, so now the natural problem would be to ask for what kind of patterns is the class chi-bounded and for what kind of patterns it is not chi-bounded. Of course, if the pattern contains a cycle, made of edges, of something that is required to be edges, then it will be no longer chi-bounded, because even in the unordered setting, it is not chi-bounded by the result of R dash. So here it will be not chi-bounded as well. So interestingly, we were also able to show that if we exclude this cross-matching pattern, so here we have an edge, here we have an edge, and no other edges, then this gives rise to a chi-bounded class of graphs. So yes, this is something that was asked by Tomon, and an interesting reason why, so this is a stronger result, right? Because we exclude less than we exclude here. Here we don't care about these edges between consecutive vertices. And here we require, in the excluded pattern, we want that there is a non-edge here, non-edge here, and non-edge here. So if there is an edge here, then something like this is no longer excluded. It can appear in our graphs. So the class of graphs excluding this is broader than the class of graphs excluding this, and still chi-bounded. So here is why this last result can be interesting. So we can look at so-called outer string graphs. So here is an example of an outer string graph, intersection graph of curves which start at a common horizontal line. We have a result with ROC that these kind of graphs is chi-bounded, and it is an easy observation that these graphs are cross-free. That it is, if we order them according to these points here, we cannot obtain this structure. So this result from the previous slide actually tells us, it implies that outer string graphs are chi-bounded. So it implies this theorem. Okay, so how this is proved? Actually, we can look at this graph. This is an example of a banana. So in general, a banana, we take a subdivision of something like this, where we can subdivide the edges by putting new vertices. And if we take this specific subdivision, that with any order, no subdivision of this, no further subdivision of this is cross-free. So how can we use this fact? There is this result by Scott and Seymour that whenever we exclude induced subdivisions of some fixed banana B, then we obtain the class that is chi-bounded. So now it follows from this observation and this result that if we exclude, that if we look at the class that is cross-free, then we have excluded also all induced subdivisions of this banana before. So as a corollary, the class of cross-free graphs is chi-bounded. Okay. However, for capped graphs, we obtain this kind of very nice bound, especially when they are ordered whole free. So while this bound here, which follows from this theorem, it will be some very large function. So I'm not sure whether I still have time to tell you something about how this is proved. So maybe I will.
We need to conclude in 2 minutes.
Mm-hmm. Okay, so maybe I will not tell you anything more about this result, but the proof is not difficult. So let me go to the conclusions. Here is the summary of our results. So first of all, we have proved these bounds for capped graphs. And then we have proved that every H-free graph, so graphs where we exclude these kind of cyclically ordered structures, can be vertex partitioned into 3 capped graphs. So this way we obtain like these bounds here, they imply these bounds for H-free graphs. Just we get a factor of 3. And then since every curved pseudo-visibility graph, so in particular polygon visibility graph, it excludes H and it excludes ordered wholes, then in particular, this bound can be applied to curved pseudo-visibility graphs. So we obtain this bound for them. And finally, we have observed using this result of Scott and Seymour that the class of cross-free graphs is chi-bounded. So the class of graphs where we exclude this crossing induced matching of size 2. So how about some open problems? First of all, we can ask whether these classes of graphs, which are mentioned here, whether they are polynomially chi-bounded. So chi-bounded by a polynomial function of the clique number. Here the function is single exponential, like for instance this one. And it would be nice to have a polynomial function, and of course this would imply polynomial functions here and here. And another open problem, which can be considered more like a research direction, is for which ordered patterns P is the class of P3 ordered graphs chi-bounded. So we know that the pattern P should not contain any cycle made of the required edges that are required in the pattern. But we have also seen some examples where the pattern has no cycles and it still gives rise to a class that is not chi-bounded. So it is not clear what the distinction should look like. Okay, I will finish here. Thank you very much. Maybe one more thing that I would like to say. We have a lot of fantastic talks during this event, but I would like to draw your attention to the talk by James Davies, which is going to happen at 3 p.m. UTC. And he will also speak about chi-boundedness of graphs with geometric representations. And in particular, he, as far as I see, he will also exclude some results of our joint collaboration. Thank you.
Thank you. We have some time for questions.
I have a very small question.
Okay, go ahead.
So you use the fact that when you're cap free, you induced banana free. So do you have examples of use in the other direction, that when you are a class that excludes some unordered structure, like an induced graph or an induced subdivision, then it includes some ordered structure?
I'm sorry, I got lost in your question.
So in your results, you went from capped free to induced banana free. I mean, the inclusion is that if this is capped free, then it's induced banana free, right?
Mm-hmm.
So you start with some class that excludes some ordered structure, and it also includes some unordered structure, which is more complicated. But do you know examples in the other direction, that you start with something that excludes some unordered structure, like an induced subgraph or an induced subdivision, but then you can use a result about forbidden ordered structure? I don't know if this is clear, but
yes, I understand. So you are asking about some specific example where this can be used to prove some interesting result.
Yeah, for unordered structure.
I don't. So nothing non-trivial comes to my mind. So, for instance, there are a lot of results where we can use, we can find, say, comparability graphs in some larger graphs, right? So comparability graphs can be thought of as excluding ordered substructure. But nothing more than this comes to my mind.
Okay, thank you. Thanks for the talk.
Thank you. We have still time for one question and possibly answer. Well, if not, thank Bartosz again. And we have a small break for preparation to the next talk.